All right, so Eneko already presented me. I'll be talking about wind waves and storm surges in the Mediterranean Sea. I just started my third year of PhD in here at the University of the Balearic Island. This picture is a picture taken in the Olympic Harbour in Barcelona. It was taken during a Gloria storm that occurred in January 2020. You can see here there's like a huge wave overtopping the coastal defenses, well, the defenses of the harbour, a dike, it's there. And this storm generated really extreme coastal sea levels with huge inundations in the Balearic Island and especially in the Catalonian coast. So what are the processes that contribute to have such events of coastal extreme sea levels? If you go to the ocean or the sea with a calm day, the atmospheric pressure is the mean at 1013 hectopascal. You stay a few hours, you will see kind of oscillations of the sea level, which corresponds to tides. In here, Mallorca, you have to stay on, you have to really be focused to see them because they're really small. And it's quite the case in the Mediterranean Sea. You have a microtidal environment, meaning that for our study, we are not taking into account tides. But if you go in France to Le Mont Saint-Michel, for instance, you'll see that from 6 hours later from now, you will have a difference of up to 10 meters in the height of the water. But that's not the case, for instance, in Mallorca. Then, when you have stormy weather, you will have what we call an atmospheric surge that will increase the level of the water near the coast. So there's two reasons for this. There's the part of the pressure, the atmospheric pressure. If you have a high pressure, generated by calm weather, nice weather, you have high pressure above the sea level, so it kind of pushes down the water, right? And then when you have a depression in a cyclone, for instance, you have a low pressure, so it means the water will come up. Then you have wind. So when the wind is going from sea towards the coast, it kind of pushes water towards the coast and inducing an increase of the sea level. That is called the wind setup. And then you have the effect of waves. When the waves get close to the coast with little depth, they will break. Everyone saw it when you go to the sea. You see the waves breaking, and they do an effect. They have this effect of breaking waves. It brings a surplus of energy and surplus of water, and this also will increase the sea level at coast. It's called the run-up that divides in two different components. The swash. The swash is the white splash that you see close to the beach. At the coastline, you see the swash go up and then the back swash go down. And then you have the wave setup, which is an average. Generally, you have to see the average sea level over more than 30 minutes. You will see that there's an average because of waves breaking within time. And this is the wave setup. And for my PhD with my research group, we focus on the atmospheric surge, so from wind and pressure, and the wave setup components in the whole Mediterranean Sea. So to do this, to monitor and measure coastal extreme sea levels, you could rely on in-situ observation, like tide gauges. You find them generally within harbours. But it's okay if you do, like, let's say, a study on the Palma Harbour. You have a tide gauge that has a long time series, and you can do a study out of this. But if you want to assess coastal risks in the whole coastal hazards within the whole basin of the Mediterranean Sea, you can do it out of in-situ observation because you have a lack of spatial coverage. And that's where we use numerical modeling. So what are we going to model? The sea surface elevation I just mentioned. So typically you go to inner harbor, for instance. You can do yourself with the scale here. You can note every 15 minutes, every 30 minutes, every hour, you can note the sea level and you will see oscillations that corresponds to different factors. Now, this was used before, and it's nice to when you learn everything. But now there's use of tide gauges, and for instance, this one works with laser. There's a beam going to the surface of the sea surface, goes back, and you have the height between the tide gauge location and the sea surface. So you can monitor these oscillations. We are looking at hourly elevations. Then we're going to simulate waves. But what kind of waves? When you think about it, when you hear simulation of waves, and so that's what I thought before getting into oceanography studies and starting a PhD, I thought I would simulate what I see actually at the sea, wave to wave, wave that waves, you know. So that's a little simulation. Well, it's actually possible with phase resolving model, it's called, and basically you are modeling what you would see at the beach. But the thing is, this is it has a high computational cost, even for a small beach, and we want to have a study that describes the wave climate and the extreme sea levels in the whole Mediterranean Sea. So it's just impossible to do it with these kind of models. So we are not really simulating waves as we all think about it. But what kind of waves are we simulating? So for instance, if you go to the sea with, let's say that's me, and that's a guy that a really trained observer that is able, just by watching, to measure the crests, so the top and the throat of the waves, like this. And you stay like 30 minutes, 1 hour, 2 hours, as long as you can, until you have a distribution, a statistical distribution of waves. Okay, so that would be then here synthesized with this PDF. So with our wave distribution during, for instance, let's say 3 hours, or it could be more. Here at the top you will have the most probable waves, because here you have the height of the waves, and here the number of the waves of that height. Most probable wave, the mean waves of the total distribution of waves, and here you have the significant wave height, which is defined as the average of all the waves belonging to this area. So it's the average of the third highest waves, and this is the parameter we're going to look at. Actually, lots of you go to the sea for field experiments. If you go diving or for surfing, whatever, you always check how's the weather and also the wave climate. You can check, for instance, here you have a snapshot of the SOCIB wave model. You could also watch the Puerto del Estado model. You should not type in Google surf forecast. These are not really good. It's 3 hours. It has really low resolution, so it's really easy. It's mapped like this, so you have the color goes for the significant wave height, then you have the direction of the waves. So that's much better than others that are simplified. And when you have, for instance, let's say in Andrach, the model says at that time you will have a significant wave height of 1 meter. It doesn't mean that you will have 1 meter waves. It means that most of them will be lower than 1 meter. Statistically, like 1 out of 7 will be about the size of the significant wave height. And if you have this wave height, significant wave height within 1 day, you might have 3 times in a day waves of 2 meters, twice higher. So yeah, you should keep that in mind if you go to the sea. Okay, so that was for the introduction. And what I've been doing for the second work of my PhD is the generation of a reanalysis, a hindcast, of wind waves and storm surges in the Mediterranean Sea since the 1950s. We use the schism model. It's a hydrodynamic-wave coupled model that is used to simulate wind waves and sea surface elevation. We are forcing the model with wind. It's the wind at 10 meter height and the mean pressure level from the Era 5 atmospheric forcing analysis. And what we did is 2 different simulations. The first one, only a hydrodynamic run, it means without waves, only wind and pressure. Then another one, including waves. So we have an elevation with the coupling of waves and without. So that allows us to see what's the effect of waves on the sea surface elevation. And so the objective is to generate hourly outputs of sea state parameter for 72 years. And that's an example. That's what you have. It's the significant wave height, wave climate. During the Medicane Rolf that occurred in 2011, we have the same for sea surface elevation. And here, for instance, I don't know if you ever heard about Medicanes. I worked on this on my first part of PhD, where you find highest wind, you will find highest waves. All right. Okay, so the stop domain study, we're using an unstructured mesh, which is an infinite mesh that is made of triangles, not squares, that has the colors. When it's red, it means that you have a horizontal resolution between 16 and 20 kilometers. It's at open sea. And when you go towards the coast, it goes up to 200 meters, so high resolution, because we want to be able to resolve some processes that occur near the coast. At open sea, we don't need that much resolution. And with this, it's already a huge mesh with almost 4,000 nodes. So that's a lot of nodes. And here you have an example of in the Strait of Sicilia, where you have a high resolution. And so I didn't say here we have an open boundary because we can't simulate the whole world. We just want to simulate the Mediterranean Sea, but you need to deal with this open boundary. We just apply hydrostatic equilibrium, which is with the pressure you have response of the sea surface elevation. The first step you have to do when you do such modeling is to validate it. So that it's not like you do the modeling and then you validate. You do the modeling, you see what's wrong, and then you comparing to in situ data and you kind of tune your configuration. So to do this, you have to validate the sea surface elevation. We do it against a tide gauge from the Tesla 3 dataset, which is a global dataset of tide gauges. And for instance, here you have in blue you have the simulated elevation, and in red the let's say our real elevation, our reality. And then we did the same for the significant wave height from wave buoy data. If you are navigating in Palma, in Mallorca, you've seen this kind of buoys in front of the Bay of Palma, for instance. And we have satellite data from the CMEMS services that allows us to have spatial coverage. I'm not going to get into an exhaustive validation of it. Overall, we have good results, especially for sea surface elevation. We have results that are as good as existing database of sea level or better. Trust me, otherwise you can read the article of the part talking about the validation. But this is a statistical indicator that takes into account the correlation, the standard deviation, and the mean between observations and simulated data. But what I wanted to show here, it's not always easy to validate because these red dots here goes for are the tide gauges that we have within the Mediterranean Sea, where we also the same. And you can see that the northern African coast, for instance, we have nothing except here, it's the Alexandrian tide gauge. Because there is no data, or it's military entities that have them, and they just don't provide it. But that's when, for instance, for waves, we took advantage of satellite data that doesn't have the same time coverage, but they have a good spatial coverage. Okay, so once we have our product, so 72 years of data, what can we do with it? Well, lots of different things, but the first thing we did after this is the computation of return levels. Anywhere you have coastal infrastructures, coastal population living near the coast, you need to know what you'll be facing. I'm talking here about coastal hazards from the sea, so the coastal extreme sea levels and the waves. And you need to know, for instance, what would be the highest wave that could happen in Saint-Malo at that place within 100 years. Because I want to, for instance, for insurers, I want this house, these buildings, insured and protected for 100 years. So that's when comes in the game the computation of return levels. So basically, for instance, it corresponds to a return level computed in Valencia, I think, south of Valencia. For instance, I say, what would be the highest extreme sea levels that could occur within 26 years? And this curve would tell me that it's 55 centimeters. The red curve is the return level computed with the elevation without taking waves, taking into account waves, and the blue one with waves. We see after what does that mean, these differences. Okay, so to compute these return levels, first you need a distribution of independent events. There's only 1 year here, but I do it with 72 years of data. The more data you have, the more robust will be your statistic on return levels. The first thing you do is you want your local maximas with a window of 3 days here in independency to make sure that you're not taking two peaks that correspond to the same storm. okay? And then you don't want to take all these events because they're not all extreme. I mean, this one, these are waves. You have here, it corresponds to the Gloria storm. You have 5 meter significant wave height. We don't want all these. So let's say it's only with one point, one coastal point. So I say, okay, I will take all my independent events above this threshold. So I have now my distribution of extreme independent events. And then what we do, so you have these dots here are the distribution of these extreme independent events. And what we do is fit a general Pareto distribution. You could fit different kinds of distributions to it, probabilistic distribution, but that's the one we're using here. And okay, so yeah, the fit is the curve from the, let's say the distribution of extreme events. And we want to do this for every coastal point within the Mediterranean Sea. So this one I did it like, okay, I say it's purely subjective, this one are extreme events, the others no. But we want to do this for the whole Mediterranean Sea, so you can't, I think we have a bit more than 110,000 coastal points in total, so it's just impossible to do it manually, so we have to automatize it. So what we did, I'm not getting into the details, but here you could have a multitude different thresholds. Why this one, why this one, why this one? So we apply a statistical method that is automatized and based on already existing statistical method, that will select kind of the best threshold that ensures that taking this threshold, the distributions fits well with such probabilistic distribution that fits with the theory. Again, if you want more details, we can talk about it later, or you can go read the article that talks more in details. And then, yeah, so we'll repeat this procedure for the whole basin. And these are the ratios for the significant wave height. Why at 20 meters? Because for the elevation, we have the elevation at the coast, at the coastline. But you know, if the waves break before the coastline, it breaks if you have a waves, I don't know, 10 meters, it will break before the coastline. But waves breaking before 20 meters, you need a huge wave that doesn't occur in the Mediterranean Sea. So you want to be sure that the break didn't dissipate too much and didn't break. Otherwise, if I took at the coast, the significant wave height would be close to zero all the time. That's why. And typically, you will find highest return level of waves. The return level is at 100 years. So that means in Menorca, let's say that would be, I don't know, almost 8 meters. Within 100 years, the highest significant wave height that you can expect within 100 years is almost 8 meters. And where you will find these highest waves is where you have large fetches. What's a fetch? It's large distances in open sea where you could have a wind, sustained wind blowing, so transferring energy to the sea surface, and generating waves. So typically here you have the Mistral wind here and the Tramontane that kind of radiates, blow a lot of sustained wind and radiates waves that gets to the northern coast of Algeria and Morocco, Tunisia. And here also you have large fetches. On the contrary, in the Aegean Sea, the Adriatic Sea, you have small distances, though you can have strong winds. You don't have enough space to let the generation and the propagation of waves across the sea. So that's where you will find the lowest waves. And the same for the coastal elevation. Typically, you will find the highest return levels of coastal elevation at the tail of the Adriatic Sea, north, where you can find here Venice. Mainly because here you have a wind called the scirocco wind that is blowing, and so what I said before, you have strong wind setup here. You have wind pushing water towards the coast. And then you will find high return levels here in the Gulf of Sirte, the Gulf of Cadiz, in the Gulf of Playa, and here near south of Valencia. Because there they have a particularity. They all share kind of configuration with the continental shelf, with mild slopes, a large continental shelf, and mild slope that favor the wind setup. So the winds the mild slope would mean the slope like this. High slope would be like this. So you have the model can, the wind pushes water to easier towards the coast, and then also the model is able to capture little depth here to capture the breaking of the waves. So you have both the components of the wind setup added here, and the wave setup. And as I said, the novelty of this work is first the long periods, 72 years. The largest was maybe up to 40 years, 41 years for both waves and storm surges, sea surface elevation, high resolution, and also the component of wave setup. At least in the Mediterranean Sea, at that scale, it's the first time we are able to assess the wave setup component. To show that our model is able to capture this wave setup, this is an example during the Gloria storm. So you have huge waves generated by intense winds. Here you have a zoom in the area of Gandia, it's south of Valencia, in eastern Spain. And you have these waves, significant wave height higher than 7 meters, that gets near the coast with perpendicular direction. Here you have the bathymetry, so that. And here you have the simulation without the waves. So this is the coastal sea surface elevation. And you have the simulation with the waves. And you can see that with winds and pressure, you do have like coastal extreme sea levels. But when you add the waves, and this is because of the wave setup effect, you can see that from 30 something centimeters, you can reach 70 centimeters. So there's an increase higher than 100% of the sea surface elevation. And well, this is a particularly extraordinary storm with wave-breaking records with significant wave height never recorded in Western Mediterranean Sea with more than 8 meters for the modern era. But it does work with lower intensity, with storms in lower intensity. And what I did here is complete the same return reverse that I showed you before, with the elevation taking into account waves and without. And then so I have my return reverse and I just do the difference. And everywhere it's kind of red, you see that the return level, it has an impact on return level. What does that mean when you want to, what does it imply? For any coastal infrastructure you want to design, you will not have the same response to it. And again, the area most concerned are the one we saw before, where you can have the combination of wind setup and wave setup. Okay, and to conclude, okay, so yeah, this project we have now provides 70 years of data, so large, long period data of wind waves and coastal sea surface elevation with an unprecedented spatial resolution up to 200 meters. And now what we're doing is trying to assess, have a more precise assessment of the wave setup contribution to extreme sea levels and compare it to what is done until now, because you're not always able, you're not always simulating with the wave setup. You can use different methods that are widely used at global scale, not only in, you can use, for instance, there's one formula that says that wave setup will be 0.2 of your waves. That has been widely used for global models, but we know that this is a huge approximation. So you have other methods and we're trying to compare them. And then with this hindcast, we have potential numerous applications such as downscaling. For instance, I want to do a nice description of the wave climate and the coastal elevation in the Bay of Palma. What I will have to do is to use a mesh really with high resolution, let's say until 1 meter at coast. Well, I need to simulate just a small area of Palma. So I will force the boundaries of this new simulation with these products. And also, it can be used in cross-disciplinary studies, like did Maria Mulecerna for her TFG, for her final grade work that investigated the effects of storms, wave storms, on the growth of Posidonia for the last 40 years. Okay, thanks. don't know what's the time.
Perfect.
Okay. Well, it's already a bit late. If you have any question, you go ahead. I can't see.
Me?
Yeah, two.
Okay, Mario.
Slide 11, I think, you show the mesh.
Yeah.
My question is, why do you go like on the ocean on the west side and on the east side you don't consider the effect of the sea
Yeah. Mm.
there and there?
You mean here you have a Detroit, you straight here, and a small one here. Yeah. It's because basically basically it's not very basic. What's the most the first simulation that we did, we closed here, so it was closed everywhere. So it means like it's like bathtub. You have a bathtub, it's closed everywhere. But then we know that the Gibraltar Strait, you have lots of processes of exchanges of water that occurs, and it's really important to model it. And once through the validation, as I said, comparing twin-city data, we would find problems and then tuning. And once we did this with opening here, because you want to, there's a lot of reasons, but it did improved the simulation way better, and we already were better than existing models. But it's true that here you have straight, but these straits, I don't know what's the dimension, but this is it's 20 kilometers at the
14.
14, okay, 14. And these are much, so I can't say if there's what would be including the Black Sea and the exchanges for this simulation. It's not a 3D simulation, so it's only a 2D simulation.
Yeah.
So, but we were already satisfied. It took It took a long time to get this configuration. I could have spent my whole PhD doing this, but yeah. Yeah, I don't know if including the Black Sea will change something. I don't think so. But I haven't studied it, so I cannot say for sure. But it looks like no, because Marta just no. Yes, Marco.
So I was intrigued by the time series for the return. Yeah, that one. So let me see if I understand it correctly. So what you have here is a time distribution of wave heights.
Yeah, every hour.
Okay.
Sorry.
Yeah, in time. Right, you have distribution of wave heights, and then what you do is you look at the you pull everything together and you look at the probability distribution function for the values of this. That looks like a Pareto distribution, whatever. I don't know if there is a reason why it should look like a Pareto distribution, but fine. And then essentially what happens is that over time you're sampling this distribution, right? Every so often you make a measurement and you're sampling the distribution. I was expecting maybe, well, I was wondering, let's put it like that, whether...
Just to be sure, the sampling distribution, you mean?
Well, you get a value that comes from that distribution.
Okay.
So you have looked at, for example, within 100 years, how often it happens that you have a value above a certain threshold. But is there any interest in looking, in trying to understand whether there is an underlying dynamics that you can say something about in terms of, so what you're doing essentially is you're drawing a random number every, whatever is your sampling time.
It's 72 years.
Well,
it's stationary. I mean, we are supposing that we...
Right, so for example, fine, it can be stationary, but it can be stationary in many different ways. So I was wondering whether there is anything you can learn by looking at things like the autocorrelations, or trying to understand what sort of dynamical system would give you a distribution like that in such a way that then you can maybe see whether the same type of dynamical system is happening in other places and make predictions that might be more robust than just looking at the past.
That would include spatial variability, you mean? Because this is made for every coastal point with its own distribution.
Yeah,
and
but if I give you this,
and
I tell you, what's the system? Can I put the dynamics on this random variable that gives me this sort of, on an average sense, this sort of dynamics, the dynamics that I see?
I think I really don't get what you mean by dynamics.
What I mean is this, for example, let's suppose that I have a coin. Okay, so these things could be 1 or 0. And then I flip the coin, and the coin is completely fair, so I get strings of 1s and 0s. And by looking at the string, I can deduce that what I'm doing is I'm flipping the coin, and every single time I have a half.
Yep.
Okay. Or it could be, for example, that this comes from a process where I know I have a Brownian particle that is tethered with a spring, and then this thing moves around, and I look at the elongation of the spring. I would get different, I can get out, okay, the dynamics of the underlying system by looking at the things, for example, like the autocorrelation function of the values, and therefore say something about what is the process that creates the values, not just looking at how often a certain value happens. I mean, I don't know whether this is something that is done, whether this is something that is absolutely stupid you wouldn't learn anything from, which could be.
I can answer.
Yeah, you can answer.
Well, I understand that you cannot answer because this is something that we never discussed before, but when you are looking at extremes, it can be shown that if you have an stochastic process and then you sample the extremes, they always fit to families of empirical distributions, Pareto and generalized extreme value. So you are doing it the other way around. So you are assuming, your hypothesis is that this is the dynamic of the system, that you are working with extremes already. That what you are sampling are extremes, and then you can fit this kind of empirical distribution. So we don't wonder about the dynamics of the system. We assume that the dynamics of the systems is formed by extremes, extremes of whatever. Okay.
It's the tail of your distribution, and you're already assuming that the tail is corresponding to an extreme.
The tricky thing here is that you need to get enough data to make your assessment, your statistical assessment, and you have to make sure that these are real extremes. For example, if you put the threshold very low, then you will be getting many points which are not extremes. Then this hypothesis does not hold anymore, because you have lots of values at the beginning of your distribution, which would be biased here. So you know what I mean.
I know what you mean, but this isn't exactly what I was asking.
Yes, I know. But the point is that we don't.
I'll ask you later.
Yeah. Okay.
For the correlation. The answer is yes. You know exactly the system.
You know the system.
Yes,
Yeah, you know the
various
system.
stocks. The
Right. Yes, but I'm
highly not
of course. But I mean, that's fine. But that's a bazooka option. I'm thinking, yeah, sure. But I mean, it would be the same as saying that in order to understand how this chair works, I need to model it from a molecular perspective. That's not the case.
I know. The question that we're asking is $1 million. The question of $1 million. I mean, what is behind it? What is the dynamics behind that? So that's an example.
No, pero funcionaría con una cosa estocástica, realmente. Claro, puede no tenerlas, pero funcionaría igual. Okay. Físicos.
Yes, look.
I have a simple question that will show that I did not understand anything. But what is wave setup?
Sorry. Let's get back to it. Did you get this graph? The difference between this one and this one? What does mean the color here and the color here? So
The elevation of the sea level is due to the wave effect on the
no,
rock.
In part. So here you have without waves. Okay, so you just have the wind and the pressure. You could do this with you have a small bathtub. You take a powerful enough ventilator, and you will see that the water goes on the other side and kind of accumulates there. So that's what's basic, really basic way to describe it. That's what's happening here. If you add waves, so here you have the scale. Here it's let's say 30 centimeter. Okay. If you have waves, so these are waves coming. Okay. They get closer to the coast, and when they reach small depth, so closer to the coast until 0, which is the coastline. Okay. When they get close to the coast, they will break. That's what you see. So we're not simulating the reality what we see, but it's an approximation of the reality. So when it gets close to the coast, it will break. Okay. Here you don't have waves. And this breaking and the dissipation on the bottom, there's a surplus of energy and the water mass at coast. And this makes that it will, in average, over time, it will also add, it will add up to the wind effect and pressure effect, so that the coastal sea level goes up. It's something that you cannot see if you go to the sea. You cannot see it because it's average over 30 minutes. You need lots of waves and sustained waves that comes and breaks. What you will see, it's what we do not simulate here because it's a really local scale. That the dimension, it's like the resolution would be we would need 1 meter and the wave resolving phase resolving model that I showed at the beginning. It's the swash. That's why you see this white splash. That's why you at the coast goes up and down. If you have a strong wave setup, the swash will be more here because the amount of water is already high. If you have no wave setup, the line where you have the swash will be a bit further down into the beach. And yeah, it will be this. So this is the mean sea level after adding the tides, the atmospheric surge, all right? And with waves coming, you will have this kind of slope here of the sea surface elevation that corresponds to the wave setup effect. And then the swash, this will not be always like this. Swash it will do around this line, it will do like this. But if you don't have wave setup, it will be around here, the splash. Okay? I'm not sure.
This is due to the elevation of the depth of the sea.
Yeah, because here you have high depth. The waves are not.
Yeah, so the wave elevates and then it breaks.
Yeah. You have specific procedures such as shoaling, and then that makes the waves. They get closer, they get up until they reach a point that here the slope is too high, and you have the breaking process that occurs. It's due to the depth. Yeah.
Okay. Thanks.
Okay, something add to that is how good has your coastal bathymetry or shoreline coastal structure has to be so your model is reliable, or how critical is that you have a good bathymetry and even coastline structure to calculate the setup?
How would be
What's the resolution you should have of that?
Yeah. Well, it really depends on the kind of coastal configuration. If you have really high slopes, you need a high resolution because the waves. If you have a slope like this, you can have, let's say, 1 point every 200 meters, because it's really low changing. So the dissipation, the effect of the wave not seeing the bottom friction, for instance, is not changing a lot from 1 point to the other. Really, you have a slope really like this, and you have the same resolution. You will not have, the model doesn't have time, let's say, to capture the process in between them. So if you have a slope like this, I have 5 points, it's okay. But if I have a slope like this, these 5 points will be only 2 points, and you don't have time. So the models doesn't capture wave setup all over the Mediterranean Sea. It only captures it pretty well when you have a large continental shelf with mild slopes. Yeah, and that's something, at that scale, you cannot really resolve it, or you have to do downscalings, for instance. Typically, for instance, that's something we are doing right now, but in the Bay of Palma, though we have 200-meter resolution at coast, you don't have a large continental shelf such as in front of Valencia. So we know that there's wave setup there when you have storm and waves, but inevitably you will have wave setup from the model that tells you that it's lower than it should be. And the thing is also that it's hard to have wave setup in situ data, something that we in our research group we might do the next summer or later. Yeah.
Okay, I think that we can stop here. Okay, one last question.
It's fair time.
I would like really to congratulate you and all the group for all this massive time series that you have generated. That it's impressive and it's really useful for the people also working on seagrasses, and we are doing a lot of collaboration already that I think it's very fructiferous. And I would like to ask you if you have looked if the mean sea level has already changed the return return times of the impacts already during this time series.
In respect to the sea level rise,
Yes.
the global sea level rise. No, that's something I didn't. It doesn't take into account the global sea level rise. These simulations. It's an effect that is expected to increase within, because the sea level rise until now has been quite low. I mean, compared to the projection and the slope of it. It's something that if we don't know yet if we're gonna do the simulations for projections for until the end of the mid-century and the end of the 21st century. But that's also something that, taking into account, we definitely change with the results, because it's supposed, all studies that have been done on how the wave climate and storm surges, the coastal extreme sea levels will change towards the end of the 21st century. There's high variability, or there's not a clear change in this part. But if you include the sea level rise, well, instead of having the mean sea level here, you will have it here, so the waves, instead of going here, they will be further. But it's something that we might apply, but not for the present climate, because it's quite small compared to what is expected. But some places around the world, I'm talking about the Mediterranean Sea. Some places around the world, it's already visible. From one picture from another 50 years, it's visible. But what is expected is would have a huge, would have a difference. But not for the present climate. We're not going to include it.
Okay, so if you have any other question, you can do it after. A bit more fresh area. So, well, thank you very much, Tim, for everybody for coming. Remember that if you want to give a seminar, just write us and we will schedule a day. See you around next Friday.
Como ciertas personas.